All right. Good morning, or good afternoon, or good evening, depending on when you're watching this. This will be the last video for this chapter. We're going to talk about periodic trends, and there's three that we'll cover in this chapter. In the next chapter, 13, we're going to cover a fourth one, which is electronegativity. So for now, just to keep it a little more simple, I'll just list these three that you should know, and size will be the first one. I won't spend much time, going over the concepts because you have the book and lecture videos for that. But what I would remember mainly is that the trend, so you have a left and right and up and down trend, and you can remember like it's going to go like this and like this for size, or what's just kind of easier is down and to the left. That's the combination arrow. So size gets bigger as you go down and left. This is, again, basically looking at comparing elements in the periodic table, right? So if we're using this as a guide, comparing different elements, going towards, francium down here in this corner is going to be bigger. And the size trend, if you understand that, the other two are related to that. So the ionization energy, which you would want to remember is the energy to remove an electron, that goes the other way. So actually, francium down here in the left would have a low ionization energy, and going up towards like helium in this corner, that would be the highest, i.e., this ionization energy. And I'll just point out that this is becoming more endothermic as we go up and to the right, which means more energy is required. So this endothermic means energy kind of required. You have to put in energy to do that. Like we saw before with the photoelectric effect, you have to put in energy to remove electrons. EA is electron affinity, and that is the energy that's associated with gaining an electron, which again would be important. Just because if something was written like this, or maybe on Alex, you have to actually write the process. It's kind of like a half reaction, like maybe like a reduction you could think about, although these are little just single like monatomic atoms, in the gas phase. So fluorine doesn't really exist like this in nature. This is just kind of a theoretical process that we can use to calculate or kind of assume what might happen if we had a single fluorine atom. But that would be the electron affinity, right? Like the energy, if we measure that for just a single fluorine gaining electron, that would be good to be able to associate with this concept. It gets complicated on how you define the energy sometimes, and this is why this is like my least favorite one to usually use, and that's why we use electronegativity more in later chapters. So the way usually it's kind of taught is that it goes up and to the right, but it's more exothermic this way. So there's more energy being released when it gains an electron. Okay, so this, because both of these arrows go the same way, and they're actually like opposite or different processes, right? Removing versus gaining electrons. So the only way to really rationalize that is that, oh, well, one of them is you have to put in more energy to remove it, and one is it's giving off more energy when it gains it. So that would be good just to kind of write down and try to remember. Okay, so again, if you want to go over any more of the details, you can feel free to email me or come by the study hall, and I can explain more about maybe the size trends with the nuclear charge and all that. But in these problems, we're just primarily trying to use these trends to predict things or put things in order. And so we want to increase or put them in order of increasing size or radius. So we want to just find the three elements we're concerned with on the periodic table. And remember, we can use our size arrow going that way. So if we went from smallest to largest, it should go silicon first, and then germanium, and then to the left, calcium. All right. Increasing ionization energy. So remember, this is what I abbreviated as IE, energy to remove an electron. And we normally would have this energy you're putting in increase going up and to the right. So we would predict that it would go, these are all in the second row, C and O. Right? Actually, this is incorrect. So I threw this one on there just to be kind of have a curveball. That's a tricky one, and just point out that these trends are general, and if you get into certain cases with certain elements, they don't follow the general trend. So the configuration of carbon is 2s2, 2p2. If we look at nitrogen, it's 2p3, and oxygen is 2p4. Okay, so let's draw out the 2p orbitals. 2 electrons in carbon. The 2p orbitals for nitrogen have 3 electrons. Looks like this. For oxygen, 4 electrons. Looks like this. All right. So I'm going to remove an electron. The trick is the actual order. The easiest is still carbon, but then what happens is if you look at nitrogen and oxygen, which one of those is hardest to remove an electron from? Well, if you recall, nitrogen has a half-filled subshell. That's particularly stable. So therefore, it's kind of like if you had everyone in their own dorm room in the same hall, everyone's pretty stoked on that. And then you have another floor in a different building where you got this one room that's doubled up, right? So you're trying to figure out, you have to kick someone out. It's a little bit easier to kick this person out because they're sharing the room. They might not be as happy in that situation, right? Again, kind of rationalizing this with electrons, but in that analogy, oxygen having a paired orbital, it would be easier to kick that one off, and that's what we find is if we actually measure the energy to ionize them, that this nitrogen has the highest IE because it's the hardest to remove that electron from that half-filled subshell. All right, so just to point out, I think, again, this is really tricky and something that you would have to write the configurations and just look at them, see if you have a half-filled or something that has a full subshell. Obviously, that's also very stable. And in those cases, you can get little kind of changes in the normal trend. So just wanted to throw that out there. Okay. Also, with ionization energy, you might have to deal with ions. And I think with this, it's just thinking about the charge would be the most common sense way to do this. Remember, again, you're going to remove an electron. So the smallest or lowest ionization energy, the one that would be easiest to remove an electron from, would be the one that's just neutral. And then aluminum plus would be a little bit harder. Aluminum 2 plus would be the hardest to remove the electron from because if you've already removed 2 electrons. So as you become more positive, your IE will always increase. You can also think about more positive, less negative. I could give you an example of aluminum, 3 minus, oops, aluminum 2 minus. If these they're not very common, probably don't really exist, but again, theoretical ions that you could make or try to calculate the energies to do that. And it would be easiest to remove an electron from something that has more extra electrons, and then vice versa as you go up. So hopefully that makes sense. And last one, electron affinity, energy release. So again, we're using the trend up and to the left, up and to the right, like energy released. So going in this down left, up and to the right, more energy is released when you gain an electron. And if we compare carbon, silicon, indium, so we go up into the right, it should be indium, silicon, and then carbon. And again, if we look at the subshells, electrons, there's nothing really weird happening. If we add an electron to each element, it wouldn't be anything, we wouldn't predict anything out of order for this. Okay, so there's some examples of how you can order things. And then the last one we have is a problem where they give you successive ionization energies, and they want to know which family, which also is the same thing as which group. So family is group, which also is the column, right? So kind of like the alkali metals are group 1, that's a family or a group. Which element or which family does the unknown element most likely belong? What we know is that as we take away electrons, it's harder to take away more electrons. And that is what the IE means. So the first IE, 1, is just to remove the first electron. IE2, if you wrote the process, which would be a good thing to be aware of how to do that, right, would be like removing second electron. That's the IE2, right? And then so forth. So the IE3 is removing the third electron, and the IE4 is removing the fourth. That's, as we know, always going to increase in energy. So the fact that these increase isn't telling us anything surprising, but what we want to look for is where there's a large increase. So we have, here's an increase, here's an increase. Oh, here's a big increase between 3 and 4, right? So there's something happening there that's important between the third and the fourth ionization energy. And this, once you kind of do one of these problems, you can just remember the pattern, and it's always kind of the same thing. But because we have this big increase from 3 to 4, that's saying that the fourth electron is much harder to remove than the first 3. Okay, so what that tells us is that there's basically the 3 first electrons are going to be what we call valence electrons, and the fourth electron is what we call a core electron. That's much harder to remove. Again, if we kind of think about like, this will get into more in the next chapter, but there's a nucleus, and then there's like these different shells around the nucleus, kind of like an onion has different shells or layers. So the outermost one is what we call the valence, and that's going to be easier to kind of peel away. And then the other ones inside will be considered, core electrons, right? Those are going to be closer to the nucleus and therefore harder to remove. And the easy way to link the valence to the group is just, it's the same number. So the 3 valence electrons are going to link to group, and this is going to be depending on which type of numbering you are looking at in your particular table you're using, but 3A or group 13 is the same thing. This would be like, for example, aluminum. So if you look at aluminum, the kind of configuration, oops, there's two. One is like this. So the outermost electrons, these valence ones here, would be easier to remove, right? So there's 3 of these. And then once you remove those, you get down into the core, which is the neon, basically, core. And that would be much more, oh, I just noticed. Writing this too fast. 2p6. So 1s2, 2s2, 2p6, neon, that's much harder to kind of break open, right? Okay, so once you find the big increase where that starts, if it starts at IE3, 3 valence electrons, that tells you the group. And that's basically it for this chapter. So good luck with the studying.